Hello, everyone. My name is Michael, and today we're going to be looking at Problem 8 from the team round of mathleague.org release 12502, which was our November 2024 high school qualifying round contest. Let's go ahead and take a look. When the base 10 fraction 19 over 90 is expressed in binary, the repeating part of this binary decimal has period n. Compute n. Now, to do this, we can actually apply a more general solution strategy, which is if we have a problem of this type, right, what we really care about is the denominator and properties that the denominator has in the base that we're converting to. Now, why is this? Well, we can note that since we're going to binary, which is base 2, 90 can instead be written as 2 times 45. And we don't actually care about the 2 part. And the reason for that is because the 2 part, for the purpose of this problem, will not impact the length of the repeating part of the binary decimal. And that's because if you divide something by 2, in base 2, that's equivalent to just moving everything one place value over, right? So that's the difference if we talk about in, for instance, base 10, the difference between 1/3 and 1/30th, right? If we divide by 1 power of the base, then everything just moves to the right one place value. 0.333 repeating versus 0.0333 repeating. There's an extra 0 there. So the 2 actually doesn't matter. So we care about what the period essentially is of 45, or divided by 45 in binary. And how do we do this? Well, the way that we can do this is by figuring out the smallest positive integer n, right, for which 45 divides 2 to the n minus 1. Or in other words, right, 2 to the n minus 1 is a multiple of 45. Now, why does this matter? This matters because let's consider 2 to the n for now, right? Let's say that we have something with a string in binary with length n, right? And consider that this is right after the point, the decimal point, which doesn't really make sense in binary, but the decimal point in our binary. So point, and then we have zeros and ones and some combination, blah, 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 all the way up. And let's say we have length n, right? And you don't have to think of it as after the decimal point, it can be before as well. Because say if this fraction had a value greater than 1, we would have numbers before. Now, this we can think of as, actually, let's get rid of the decimal, and let's just say that these are the first 12 values before decimal points. So obviously not directly applicable to 19 over 90, but then we can think of this, these n digits, right, is we can express this as some combination of 2 to the n plus 1 plus 2 to the n minus 1, plus 2 to the n minus 2 plus 2 to the n minus 3 and so on, plus 2 to the 0. And we either have 0 or 1 times each of these, right? 0 or 1 times each of these, depending on whether the digit corresponding to that place value is 0 or 1. Now, if we now move this n places to the right, which is now essentially putting that point back in front over here, then this value would be equal to whatever that sum is divided by 2 to the n. Now, the reason that a period of n works is if we take this block right here of n digits in binary and we just repeat it over and over again, then we create an infinite geometric series, right? And the infinite geometric series has a common ratio of, if we consider the block a quote-unquote term, a common ratio of 1 over 2 to the n. Well, an infinite geometric series with a common ratio of r has a value of its first term divided by 1 minus r, right? So if we consider this right here, the first quote-unquote term, right? And it can be shifted over by any number of place values, remember, by any number of factors of 2 in our denominator. Let's just call this entire first term x, right? If we divide x over 1 minus 2 to the n, right? Sorry, 1 minus 2 to the negative n, because we are divided by it, right? And we multiply by 2 to the n on the top and bottom, then that gives us 2 to the n times x over 2 to the n minus 1. And we see that the denominator is now 2 to the n minus 1. So we can always, by finding, right, the least value of n for which 2 to the n minus 1 is a multiple of 45, or more generally, the greatest factor of the denominator with no powers of 2, we can then write that as an infinite geometric series in binary with n terms in each block, and the blocks being the quote-unquote terms in the series. So if we check the powers of 2, this is actually not that difficult, because if 45 has to be a divisor of 2 to the n minus 1, then that means 2 to the n minus 1 either has to have a units digit of 0 or 5. 2 to the n is even, so 2 to the n minus 1 has to have an odd units digit. Therefore, 2 to the n minus 1 must end in 5, so 2 to the n must end in 6. Well, the first three values of 2 to the n that end in 6 are 16, 256, and 4096. It's easy to check that 16 and 256 do not work, but 4096 does, and that is because 4095 is a multiple of 45. And 19 over 45 can actually be written as 1729 over 4095, which is equal to, wondering, that would be 2 to the 10th plus 2 to the 9th plus 2 to the 7th plus 2 to the 6th plus 2 to the 1st. That can't be right. That ends up being even. Plus 2 to the 0. Right. Plus 2 to the 0 over 4095. And remember, it's just not 4096 because this we've already technically, quote unquote, turned it into an infinite series. But this numerator would be, if we wanted to actually convert it into a binary decimal, we could use the numerator and remember to shift over by one place value. But we now know that 2 to the n minus 1 equals 4095. So that means that 2 to the n equals 4096. And therefore, the desired value of n that we are looking for is 12. I hope that was an informative presentation, and thank you all for watching.
This is Tim. Hope you're enjoying our videos. If so, you know what to do: like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.